What if the universe just handed us a clue, one hidden in the faint glow of an interstellar traveler, and almost no one noticed? What if a shape stretching toward the sun instead of away from it is trying to tell us something extraordinary? Before we dive in, make sure to subscribe, because what you're about to hear comes straight from Dr. Avi Loeb's newly published article, and it may rewrite what we think we know about interstellar debris. For weeks, astronomers watched 3I Atlas as sunlight sculpted its dusty envelope. But as November progressed, something about the images felt off. The coma did not trail behind the object in the usual fashion. Instead, it ballooned into a soft teardrop glow that extended toward the sun, an orientation comets should not have. And that unexpected geometry triggered one of the most intriguing theoretical questions in recent interstellar research. But here's where things get stranger. While photos painted one mystery, the JPL Horizon system added another. Their tracking revealed a subtle but persistent non-gravitational acceleration acting on 3I Atlas. It was incredibly small, just 2/10,000ths of the sun's gravitational pull, but it behaved in a remarkable way. Its strength diminished exactly with the square of the distance from the sun, mirroring the gravitational law itself, which meant something profound. No matter where 3I Atlas moved in its orbit, the ratio between the push it received and the sun's pull remained constant. This consistency is unusual. Most comets experience non-gravitational forces when they shed gas or dust. But those forces fluctuate dramatically as material erupts unevenly across the surface. 3I Atlas, however, displayed a perfectly scaled acceleration, as if following a clean mathematical rule rather than chaotic outgassing. That's when Dr. Loeb presented a striking hypothesis. Imagine, he suggested, that 3I Atlas is being nudged gently away from the sun by some internal process, maybe mass loss, maybe something else, while a cloud of tiny companion objects surrounding it feels no such push. If these smaller bodies aren't experiencing the extra acceleration, then relative to 3I Atlas, they would start drifting slightly closer to the sun. Over time, this differential movement would create a cluster stretching sunward, exactly like what the photographs reveal. To make this clearer, Dr. Loeb framed the physics in a clever way. Treat 3I Atlas as if it orbits a sun whose mass is just a hair lighter by the same tiny fraction that defines its additional acceleration. The spacecraft-like effect wouldn't change the comet's path dramatically, but it would shift its energy balance relative to small objects nearby. The result? Those untouched fragments would hold more gravitational binding energy than 3I Atlas. Even if they began with identical velocity and position, they would gradually drift to a slightly smaller orbit, settling closer to the real sun than 3I Atlas does. But here's where things click into place. At the object's current distance, roughly 270 million kilometers, a displacement of only 0.0002 of that range puts the fragments about 54,000 kilometers closer to the sun than the main body. That modest offset translates to roughly 0.7 arc minutes on the sky. And that number is not random. It matches almost perfectly the sunward glow seen in the Hubble image from July 2025. For a hypothesis, that is an exceptionally tight fit. If such a swarm exists, its geometry would behave predictably. The mini objects, unaffected by non-gravitational forces, would always appear shifted toward the sun relative to 3I Atlas. As the interstellar visitor arced toward perihelion, the fragments would seem to converge toward it. And as the object traveled away again, the configuration would reemerge, unchanged in orientation, unchanged in scale. This is exactly what the observations show. But the theory gains even more weight when you consider the brightness of the coma. A single comet-like object has limited surface area. But imagine a trillion tiny bodies, no larger than pebbles or grains, surrounding it. Even if their combined mass were only 1,000th that of 3I Atlas, their collective reflective surface could be 100 times larger. That means most of the light we see around 3I Atlas could be shining off the swarm, not the object itself. In fact, based on the Hubble data, up to 99% of the reflected light could come from these companions. But here's where things get even stranger. If this phenomenon truly arises from a swarm of non-evaporating fragments, we must confront a deeper question. Where did they come from? Were they once part of 3I Atlas, shattered during its interstellar journey? Are they primordial debris from another star system, material older than our sun? Or, in a more exotic interpretation, could these fragments represent something beyond natural rock, perhaps remnants of a disintegrated artificial body? The article doesn't claim this, but the open question invites speculation. What makes the scenario compelling is how elegantly it matches the observations: the sunward teardrop shape before and after perihelion, the steady scaling of non-gravitational acceleration, the brightness distribution, the arc-minute-long glow. These pieces form a coherent pattern, one that aligns almost perfectly with the swarm model. And yet, like all good science stories, this one ends not with certainty, but with the invitation to ask more. If we discover that these fragments are not ordinary rock, what would you want astronomers to investigate first? Share your thoughts and don't forget to subscribe for more deep space mysteries right here on Nebula Signal.